Hello? Cool. Hi, everybody. Thanks for coming straight after lunch. I appreciate it. Today, we're going to talk about DeFi defense mechanisms. So first of all, DeFi defense mechanisms, specifically economic security, is our focus at Chaos Labs. So a little bit about the company. Our mission is to protect Web3 users through scalable and verifiable simulations. So we'll get into what simulations means in just a second. Since launching the platform, the simulation platform and the economic security platform, we've already started working with some of the larger protocols in the space who are adopting these techniques. So some of the customers include Aave, Benki, DYDX, Chainlink, Uniswap, Avalanche, of course, and Osmosis. So really, when you think about security or economic security in the context of decentralized finance, we view it as a stack. So at the bottom of the stack, you have developer testing. When you're developing a DeFi protocol, say a borrow and lend protocol, you want to make sure that everything is going as planned in the face of adverse market conditions. So for example, a lending protocol, you want to make sure that your liquidation mechanisms are working properly, even when there's high volatility in the market or prices are rapidly decreasing. So we have tools that are for developers who are creating a protocol, adding a new feature, or extending functionality. One step up the stack, once something is done, you need to do a proper mechanism audit. So you have your feature, you might bring in a smart contract auditor to look at to actually go through all of your code and read it, make sure there's no reentrancy, no faulty business logic. But how do you test that your DeFi protocol that could be dependent on perp exchanges, on spot exchanges like Uniswap or Curve, how do you test that all of these mechanisms are working end to end? Once you test for correctness, we can get more liberal. We can start working on protocol optimizations. So optimizations, for the most part here, when you're talking about economic security and risk, there's a trade-off between capital efficiency, which is usually translated into revenue for a protocol, and risk exposure. So a good example of this, of an optimization you might want to do as a lending protocol, is you want the collateralization factor to be as high as possible for loans that you're letting take in the application. What's the business logic for that? Well, the larger the loan, for a lending protocol, the business model is interest rates off of that loan. So your top line revenue is increasing, which is great. But the larger the positions that are opening against this collateral, the more risk you face. And when is that risk actually realized? The risk is realized when, let's say you deposited token A as collateral. Against that, you're lending token B. When token A decreases in price faster than token B, the protocol for that position can get into a situation where the liabilities of the protocol are larger than its assets, and if this happens in a protocol-wide fashion, that's how a protocol becomes insolvent. And then the last thing is monitoring and observability. So you have a process in place to do a protocol optimization. You've tested the mechanisms, but risk, the best type of risk that you can do is proactive, especially in the world of immutable contracts and applications. When something is going wrong, it's usually too late, or there's actually not much that can be done in real time. So you want to be monitoring market fluctuations, positions within applications at all times to detect any anomalies or weird behavior that might be an indication that something is about to happen. So let's think about this a step further. I think one of the goals for this talk is to understand what the difference is between economic security and more traditional cybersecurity, which is usually a traditional smart contract audit. So when you go get your protocol audited by a CertTech or a PeckShield or many of the audit firms that exist, what they do is they put a pen tester or a smart contract engineer looking at your contracts, querying them, interfacing them, maybe writing a few scripts to do things end to end. So this is wholly focused on the code that you're writing as an application developer. But what you can't actually orchestrate in that environment is all of the dependencies of your application and the data that it consumes. So what does this include? Oracles. So how are you going to mimic now a Black Thursday type of price trajectory on an asset? It's actually really difficult, especially if you're dependent on a Chainlink Oracle. You don't own that infrastructure, and actually getting these flows is a challenge in itself. How do you model network congestion and fees? So what if you're assuming that a liquidation happens when it needs to happen, but in production that's not the case? Usually volatile markets means higher network congestions, everybody's trying to move out of their positions, it might take a few more blocks than you expected, then the difference in the execution price of the liquidation could be much lower than what it needed to be. So how do you do that? Others, liquidity providers. As a DeFi protocol, liquidity is oxygen for everything that you do. In your testing environment for your application, you don't control the liquidity that's in a given uni pool or in a curve pool. So the levels of liquidity here really matter. It's slippage, it's the depth of the pool. You don't really have a way to test that when you're spinning up your local test environment. And then lending and leverage venues, this is more application specific, but if you're building a DeFi application that's highly composable and you're using and interacting with different DeFi protocols, so different states in those applications can have dire effects for your application as well. So this slide is like the easiest, I think, for everybody who's in this room. We know what the risk is and what's at stake in DeFi. It's just every week you can refresh your browser and there's a new DeFi exploit. I just actually kind of gave up a few months ago on trying to update this because every week there's something bigger and larger. So some of the larger ones here recently are Euler, 100 Finance, but Level Finance, but the list goes on and on. So to bring all of this together, like when we're thinking about security for DeFi applications, the way we view it is sort of like the Swiss cheese model. You don't have any solution that's a silver bullet, but if you use all of them, you have a pretty good chance of increasing the threshold for attacking your application significantly. So the top is a security audit. We all know what that is. Usually that goes together with some type of penetration testing. Another layer in the stack, which has become recently more popular, is formal verification. So this is the process of taking your application, decomposing it into an abstract syntax tree, and testing rules and logic in your applications to make sure that your code is doing what you want it to do from a verification perspective. And then there's economic simulations. This is orchestrating the whole environment around your application to see how it's going to behave under different market conditions with different agents interfacing with your protocol. Expected agent behavior and also malicious. So what's unique about chaos or the simulation environment we provide, and why isn't this trivial to do alone? So most users who are trying to test the economic validity of their applications do one or two things. Some might try to recreate it in like a Python or a MATLAB or an R environment and say, this model is similar to what I'm going to see in production. In our experience, the more that your model differs from what you're going to see in production, the less useful it is. There's a well-known saying for modeling that all models are wrong, some are useful. So if you're recreating this in an off-chain environment, we could debate whether or not you're actually doing much here. And then the others is spinning up like a regular fork on your machine. Again, you have all the issues of, yes, you get a snapshot of the blockchain, you get a snapshot of accounts and liquidity for the block that you forked from, but you don't have a toolkit or ability to orchestrate the environment around it. So at Chaos, we have a bespoke cloud environment. We allow you to fork any EVM-compatible blockchain and Cosmos as well. And we give you the tools to orchestrate the state. So everything that we went before, oracles, network congestion, spinning up agents with specific risk attributes and behaviors, whatever you need to make the scenario that's most relevant for your protocol, you do that quickly on the platform. You can run parallel simulations at scale, Monte Carlo if needed, and you have access to all of that out of the box. You don't need to do all of that DevOps, all of that cloud work, all of that product work to actually build this infrastructure to support. So that is one environment, is the on-chain fork, which we just spoke about. Another one is a Chaos EVM. It's EVM compatible, written by the team. The idea here is to optimize performance. So really the two use cases for these type of simulations, one is the security perspective, which is making sure that things work, making sure that you're safe in the face of different attack vectors. The other is really optimization. So you have risk parameters within your protocol. You want to optimize them. A little bit earlier, we spoke about the trade-off between capital efficiency and security. Setting collateralization factor for a protocol like Benki or Aave is a really big deal, right? Because again, we say it's affecting top-line revenue. And the flip side of that is the security implications. So you want a data-driven approach to be able to make these decisions within your applications. What we do is we run Monte Carlo at scale. We look at historical price trajectories. We use volatility scalars to even make them more extreme. And we have a utility function for each protocol, which shows the perfect trade-off between risk exposure and capital gains. So a little bit, kind of like to make this less abstract, we spoke about a cloud environment, a little bit of how it looks. We have these catalogs that you can run that are preset. So previously, what we see here in the screenshot is a lot of the work that we've done with Maker and Aave. So these are kind of preset catalogs. It could be price trajectories, the network congestion. It could be token drops of specific assets. It could be DPEGs. And what this whole platform allows you to do is test against liquidity attacks, market manipulation, black swan events, so a USDC depeg, for example, volatility, general and extreme, and high network congestion with high gas fees. For the monitoring, we provide a monitoring platform. The focus here is monitoring financial risk. So this could be fluctuations in market liquidity, big positions, or very large leverage that is opened suddenly within a protocol. Anything that endangers the solvency of the protocol. The definition of this differentiates between a perpetual exchange to a borrow-lend protocol to an options protocol and so on. So to kind of recap the whole parameter optimization question, usually it all boils down to making a choice between mitigating our portfolio risk from a protocol or from a user perspective, or increasing leverage or the ability to kind of maximize capital efficiency. Now for the rest of the conversation, if we spoke about in the beginning about risk parameter optimization, that is like classic risk management that if anyone here is familiar from a traditional finance background, these stress tests, Monte Carlo at scale, it's stuff that you've seen before and it makes a lot of sense. But in DeFi, when we're thinking about risk, there's this other vector, which is the economic security. Now, the kind of base assumption here is when we talk about economic security is how does a malicious actor who wants to profit from your protocol, how could they behave? Now, until recently, or I guess in the earlier days of DeFi, you could argue whether or not this was an attack or not, but there were things such as use of flash loans in a lot of protocols. They didn't really think about how those could be used as a tool to kind of profit against protocols. Today, they're a little bit more sophisticated. We're seeing attackers come with significant amounts of capital, I'll say, from home. Okay, and this could be individual groups. You know, there are rumors about nation states, but you see attackers that are well capitalized and able to manipulate markets even with significant size. So just like to give an example here, we're going to run through an example, which is the Mango market attacks, which is a classic market manipulation attack. We're going to run through the steps, talk a little bit about how it could have been mitigated or potentially stopped, and then we're going to touch on a few more interesting aspects of this towards the end. So what is Mango Markets? Mango Markets is a perpetual exchange based on Solana. October 2022, an attacker who has since then doxed himself as Avi Eisenberg, profited $115 million. In one sentence, Avi recognized that they were using the native Mango token as collateral enabled it as collateral for the perp exchange, and realized that with relatively little capital, he could cause a lot of damage. So let's break down the attack. In this attack, Avi Eisenberg has two accounts that are in his control. Account A, which is initially funded with $5 million USDC. And he uses that account to basically create a perp, a perpetual order, a sell order, for 483 million Mango units on the exchange. So already here we see that he already has $5 million. This isn't trivial. I don't know how many of you have $5 million just laying around for trading or messing around with a perp exchange, but obviously he's very well funded here. Now Avi has a second account. Let's call it account B, also has $5 million USDC. So at this point he has $10 million capital that he's bringing from home, and he bids on A's initial perp sell order for an average price per unit of 0.0382. And you can see here the chart for that time. Now, account B has a perpetual exchange position on the Mango asset within the Mango Markets protocol. And Avi recognizes, hey, this is like a low float, low liquidity asset. I can pump it. So he goes to mostly all of the DEXs on Solana at that time. Also, I think as part of this attack, some centralized exchanges as well, and starts pumping the price. There's low liquidity here, so he's able to pump it around 30x to bring the spot price of Mango to 0.91. So now that the price is pumped and we have a new price established, let's look at the math. Account B is in the green. His unrealized P&L is about $421 million after the pump. And he uses this unrealized P&L to borrow assets from the Mango market protocol, essentially draining it of all high-quality collateral. Now, after the attack, Twitter starts going crazy. Mango starts dumping again. You have account B who's borrowed all of the high-quality assets out of Mango. Account A's sell position is still open, and it's actually in the money now, and it's worth 12 million. There are no more assets, so the position can't be closed in Mango. But this is really kind of the cherry on top here. So how could this have been prevented? So we have the simulation platform. Another tool that we have is the Chaos Labs asset protection tool. Now what this does is it's a model that has two jobs. The first job is to quantify the costs of an attack. The cost of an attack is a really tricky one because it depends on the asset. So if you have a token that only exists on DeFi, on blockchains, the model for calculating the cost of manipulation is different than if you have an asset which is traded heavily on centralized exchanges as well. So this is part one. How much does it cost me to move the price of asset X from A to B? The second part of this is what is the profit vector? So let's say I know that it's $30 million to pump a price 30x. Is it worth it? How am I going to realize profit here? So here you can see the UI. This is a private tool. We'll get into the interactions with Avi Eisenberg afterwards, but obviously, like in the wrong hands here, this is a P&L and a roadmap to detect and scan what assets are vulnerable and viable for profitable attack vectors. This one right here is configured for the Aave protocol. So it's manipulating an asset that's listed in Aave and then realizing that profit against Aave. But we do the same type of things for Benki and other protocols that we work with as well. So the tool, the model runs. Whoever's interested about the model, we can discuss afterwards. But the output of the tool is as follows. It's a matrix where this is blurred out, but the x-axis is the price pump factor. So you look at an asset, its current price, you want to pump it 2x, 3x, 4x, 5x. And the y-axis is the amount of capital deployed. So in Avi Eisenberg's attack, he had at least $10 million, more actually, to do the attack. And what we think here is that we want the cost of corruption of an asset to be lower than the potential profit when it's actually, the cost of corruption to be higher. When it's lower, that's a pretty good signal that this is worthwhile doing. Depending on how much higher it is, will usually dictate if this exploit vector is actually realized. So let's look at an example here. Let's say that we are a lending protocol. Let's do this. A lending protocol that has asset A. Asset A has a liquidation threshold of 70%. Now let's see, and the price manipulation costs 150 million. So now let's see the breakdown and the delineation between the costs of the pump and calculating the attack vector via the protocol. So for here, we're going to assume that it's a lending protocol. So we have asset A has a liquidation threshold of 70%. So the attacker comes from home, he's well capitalized or she's well capitalized, and they supply $120 million worth of the collateral asset. Now there's a 70% collateralization ratio. The attacker can borrow up to $84 million. And we said that the price pump is about 150. So the attacker needs about less than actually $80 million to complete the account, totaling $180 million in capital. Now, we have the funds that are required in order to do the pump. Now we can calculate, after we pumped, we have new credit within the protocol. We can extract even more assets from the protocol. So the calculation is 120 million, which was the original deposit, times the 70% liquidation threshold, times 4, which is the target pump, minus the 84 million that we already borrowed, and we have $252 million in profit. So the P&L for this attack is 250 million minus 180, 72 million in profit, 180 million upfront costs. It's about a 44% return, potentially attractive. For something in 5, obviously there's high risk, and we could talk about the risks, but this is not a joke. I think that there are some attackers that would look at this and think that it's worth it, and the more capital you have at home, the more viable this is. So the numbers change accordingly. Let's see how this could have been mitigated kind of pretty simply just by adjusting the liquidation threshold of a collateral asset. So let's say the LT of a collateral asset is 50%. Before it was 70. The attacker supplies 120 million. allowing them to borrow 60 million against a deposited collateral asset. Now, in order to reach 150 million, the attacker needs an extra 90 to complete the attack. So the total, if you look at what the capital requirement from this attack, is $210 million. Now, if we're looking at the kind of simple calculation for the P&L, so you originally deposit 120 million, you have a 50% liquidation threshold, and you're pumping 4x, but you already withdrew 60 million against that, so the total is $180 million. This cost you $210 million to execute, so now the attacker has actually lost money. We've eliminated this attack vector. Again, you can play with the numbers here and get to a sweet spot. You don't need it to be necessarily minus $30 million. You can be more lenient, but that also depends on how you view the volatility of the market. So this is an example. Like we spoke about Mango, we spoke about a lending protocol, kind of circling back to Mango, what could have been done. And it's actually very similar to kind of the mitigation that we saw here. I think the first thing here, which is obvious to everybody, is just avoid listing low liquidity assets as collateral on exchanges. That's number one. It never ends well, even if it's your application's native token. Creating utility is important, but not at the cost of endangering all your users. But now let's talk about how applications in DeFi consume data. So if a price is pumping 5x in a single block or in a minute, that's unnatural. And it's likely either bad data, a wick, or something malicious. So as an application developer, I think we tend to take everything that's coming from Chainlink or other oracles as an absolute truth. But should we be doing that? Because there are some prices or some movements in prices which are clearly wrong, and wrong is very contextual, but that is something that for every application developer needs to think about separately. Now, kind of this idea of looking at a price oracle and deciding like what is a valid transition or what is a valid jump in price, kind of you can think of this as applying like a risk engine to your oracle. No longer taking everything that Chainlink or different oracle providers providing as absolute truth, and define what is an illegal state transition. When state transition is talking about the price moving in between publications to the feed. So this is very common, like in CeFi exchanges. It's not that oracle providers don't do this. Some of them do, and we're seeing it more and more with the oracle providers that we work with. But this is something that you, as a developer, you need to ensure is aligned and working for your protocol needs. Just like a trivial kind of differentiation is like if you have a perpetual protocol that allows very high leverage, you want really low latency on the application, and you actually maybe don't want to give up on the freshness of the data, even if it's really volatile or violent price feeds. If you're a lending protocol, maybe you're okay in times of high volatility, as an example of using a longer look-back period and kind of smoothing the price, because real time may be less critical, depending on the application and architecture of your protocol, than for a low latency derivative protocol. Okay, wrapping up. So there are a bunch of other kind of practices here. Again, if this is interesting for your app, come and talk to us. And then this is just like the last thing is a double-edged sword of DeFi. So during this time, we were making, after the Mango attack, Avi attacked Aave as well. And he was kind of looking at all of the contributor discussions within the forum, also kind of subtweeting one of our team members. So you want to be as transparent as you can with your design and the trade-offs that you're doing. It's not always possible because you have both sides that have access to the same information. So this is just kind of the last piece of advice is be careful in what you're putting out there. Cool. If you guys are working on risk parameters or DeFi applications, we'd love to chat. We support derivatives, borrow land, over collateralized stablecoins, and DEXs. We're here. Thanks for coming today. Thank you.